I'd like to thank everybody here for giving me the great chance to speak today here. So, as Jakob said, my name is Falk, and today I want to tell you something about exploring stringy geometries with double field theory. And so, this talk is mainly based on a project I have done during my time as a PhD student in Munich, and it was done with Ralf Blumenhagen, so with Pascal de Busque, who is now a PhD student in Munich, and also with my supervisor, Dieter Lüst. And I started my first year as a postdoc with the University of North Carolina in Chapel Hill. But at the moment I'm on the leave, so I'm for 1 year with the City University of New York in New York. Okay. And so before I start with all the details about double field theory, I would like to give you a short motivation, so why I'm really interested in the theory. And so all of you know, of course, that we can have different perspectives on string theory. So on one hand, we can look at the string theory as a theory on a worldsheet, so as a conformal theory on a two-dimensional worldsheet. And so there are different kinds of superstring theories, for example, type 2A and type 2B. But then we can also look at it from the perspective of an effective field theory, which lives in target space. So we neglect all the massive excitations, and so, for example, we get a supergravity description. And normally the supergravity description is very convenient to use for phenomenological models. So, for example, we could study string inflation or some standard model-like setups. Yes, sorry.
Isn't it rather that you integrate out all the massive fluctuations?
Yeah, exactly. So you are really interested only in massless excitations.
Yeah,
so
it's not that you neglect them, it's that they're integrated out.
Yeah. So but you do not have them anymore as really propagating freedom, degrees of freedom in your effective theory. Thank you, for the comment. Okay. So, but you know that's not the complete story, because there is something very intriguing in string theory, so that we have dualities in string theory. So, for example, we have T-duality, which links type 2A and type 2B, or the two heterotic theories. And so there's also S-duality, so which links some strong or some weak coupling regime of a theory. And now, of course, it would be great to make these dualities also accessible from the target space point of view. So T-duality means target space duality, so it links different target space geometries, and we can find it a little bit also in supergravity when we use the so-called Buscher rules, so which tell us how we can describe a T-dual version of the theory when we T-dualize along one U1 isometry. However, they are quite complicated, and it's not really a manifest symmetry of the theory. And this is exactly where double field theory comes in. So double field theory really tries to formulate a theory which makes T-duality on the torus, that will be very important for the rest of the talk, a manifest symmetry of the theory. And so I want to place my talk exactly at this interface here. So I want to tell you how you really get double field theory, and not only the standard double field theory, but an extension of it from the worldsheet perspective, and what we can then learn from this theory. So that's the plan for today. So let me get a little bit more into detail. So first of all, I would like to give you a very, very short review about double field theory, so what it is like and what it consists of. Then I want to make some advertisement for the theory. So I want to tell you what it is good for, why we really want to use it, what are the problems in this formulation, and also partially how can we solve these problems. And so this question for solutions for some of the problems will bring us to another version of double field theory, an extension of double field theory, namely double field theory on group manifolds, or more technically, on Westermino-Witten models. And we will really derive the theory starting from a worldsheet description using closed string field theory. And then the results are quite bulky and not very handy. So we will reformulate them in terms of a generalized metric, which makes them much easier to use. And finally, I will come back to the problems I've mentioned, and I can really then show you how some of them are solved in this new framework. And finally, I want to close my talk with a short summary and short outline. Okay. So all of you know the story for supergravity. So when we want to approach supergravity from string theory, normally we do the following things. So first we look at closed strings propagating in some d-dimensional, where d is a critical dimension, dimensional flat space. So like the one you can hear, the strings, and they have in general some momentum along they move in the space. And so then we are interested in some low energy effective theory. So we integrate out all the massive excitations. So we take them away and only keep the massless ones. And finally we assign some fields to these massless excitations, counting how many string strengths we have. And so we can, for example, assign them to a metric or a dilaton field. And then we calculate the CFT scattering amplitude, and we match it to the amplitude of an effective theory. And at the end of the day, we, for example, get this NS action of supergravity with a well-known curvature scalar and a kinetic term for the dilaton, and also some gauge fields, the so-called H flux. So this is well known, but what happens now in double field theory? So the idea in double field theory is now not to look at some extended space, but some compact space instead. So, and still we want to have it flat, so flat compact space, we take a torus, for example. So, and on the torus, again, the string can move along the torus with some momentum, as you see here, but in contrast to a point particle, the string can also wind around the torus. So we get an additional degree of freedom, which is called winding excitations. And now we want to do the same as we did for supergravity. So we want to have some conjugate variables to the momentum, which is the position. And now we also need some conjugate variable for the winding, which is the so-called winding coordinates. So we now get the double number of coordinates, and we combine them into a doubled vector, which is this capital X. So this is the whole story, and this is also why we call it double field theory, because we have a double space here. And then we repeat the steps from supergravity in the fancy language of closed string field theory, and at the end of the day, we get this effective action here, which you can see here. And this looks very nice because, first of all, it looks more compact than the one I've shown you on the slide before, because now we have here an integral over the double space, and we have this object here, which is called a generalized Ricci scalar. So it really looks a little bit like an Einstein-Hilbert action. And so this generalized Ricci scalar depends on the so-called generalized metric. So it describes curvature of this generalized metric. And this is the action. We will have a detailed look at this in a second. But I want also to show you that we have to put in an additional constraint. And this is something new for double field theory, which we do not have in supergravity. So the consistency of the theory is only guaranteed when we put in the so-called strong constraint. So, which is this differential operator, and it has to annihilate all physical fields, all parameters of gauge transformations, and arbitrary products of them. And there's also a little physical interpretation behind this constraint. It tells us that we cannot have momentum excitations and winding excitations in the same direction as at the same time. So look at this picture here, everything is fine. Momentum is in this direction of the torus, winding is in this direction, so the strong constraint is not violated. And I will show you later on really how the strong constraint arises from string theory as some version of level meshing. But for now, it's okay to remember this point. Okay, so let's have a closer look at
have target space quantum calculations been really done? I mean, the traditional calculations until now have always been with the usual supergravity.
Yeah.
To compare with roll shape. But are you suggesting that this now has been done, is being done with the
it is so first of all, this theory,
double geometry setup?
This theory, first of all, is a classical theory. So when we derive it, it is really classical. And then one can, of course, start to try calculate quantum corrections. But then one has to calculate these corrections with implementing the strong constraint, which really then reduces half of the additional space-time dimensions, which makes them non-dynamically, and then you again get this d space-time dimensions.
So before you set out to calculate amplitudes, you already do the reduction to the usual.
Yeah, but
field
so,
theory.
but so only one special solution of the strong constraint gives you the usual supergravity in this picture here. And it becomes even more interesting in the new theory I present you. There are solutions for the strong constraint which does not give you supergravity at all.
So my question is, are amplitudes computed in such theories or not?
So at the moment, people starting to do this. So, and but I would not say that there is some complete finished picture about this. So people try to start to calculate amplitudes, also not only in double field theory, but also in exceptional field theories, which makes this S duality also manifest and combine it with U duality. So I heard you talk about this. So there is progress in this direction.
Okay.
But still, it's not 100% clear. So what we are really interested in is first to understand the classical level. And this alone is quite complicated. Okay? Okay, let me come back to the action. So I've already told you about this doubled space here, over which we are integrating. Then we have also a generalized dilaton, so which combines the normal dilaton with the square root of the matrix determinant. And we have this generalized curvature scalar. And we can write it down, as I already mentioned, in terms of the generalized matrix. This is this H here. And so in this equation, so we also have a partial derivative, a double partial derivative, which acts on the momentum and on the momentum and on the winding coordinates in the natural way. And finally, we have this generalized matrix, and in this generalized matrix, we find all the fields we know from standard supergravity. So we have the metric and we have the B field. But the interesting thing is so that this generalized metric is an object in ODD. So meaning that it is a transformation which leaves the ODD invariant metric, namely exactly this guy here, which has a signature plus and minus when we rotate it, invariant. And this is interesting because ODD transformations implement exactly T-duality transformations on the torus. Again, everything on the torus. And so that's why, because we use this metric also to contract these indices, the theory has a manifest global ODD invariance. And this is exactly why people say double field theory makes T-duality manifest, because it has this ODD invariance and we can rotate it and still have the same theory. So it makes it manifest. That's the idea. Okay. And now we can come, of course, to gauge transformations. So because I've shown you an action, and of course the natural thing is to ask what are the symmetries of this action. And there we have, again, like in this geometric picture, we can write down all the different symmetries in terms of a generalized Lie derivative. So we can write down the diffeomorphisms and the D-field transformations, both in terms of this generalized Lie derivative, which you can see here. And again, you see you have the generalized metric and this derivatives, everything in the doubled space. And we will also find something which is called beta field gauge transformations, which we will not have in supergravity. And the reason for this is that these are the T-dual version of B-field gauge transformations. And because supergravity has no really T-duality manifest, we do not really see them explicitly in supergravity. So, and the natural thing, of course, is now to check whether this gauge algebra closes, so it has to close to give us a consistent theory. So we look at the commutator of two gauge transformations and should get another gauge transformation, which parameter is given in terms of the so-called C bracket. So again, a generalization of the normal Lie bracket in ordinary geometry. And so this is really the case, but only if, in general, the strong constraint holds. So when we violate the strong constraint, so you see why the strong constraint is so important, then, in general, the gauge algebra does not close anymore. So we see we need the strong constraint in one way or another. Okay, so this was the short review part. And now I really want to make some advertisement why it's interesting to look at double field theory. So, and to do so, I want to present you the landscape of different string backgrounds. And it is well known that string theory has not only one background, but there is a vast number of different backgrounds around, which we can use to look or study string theory. And some of them can be treated in some kind of a large volume regime. So, and we can use supergravity to describe them. So there are, for example, Calabi-Yaos, and there are backgrounds with fluxes, and there is a very, very sophisticated set of tools we can use on this kind of backgrounds. So, however, I also told you that there is now double field theory plus the strong constraint, and I've shown you that we have this ODD symmetry. So we could start from something which we know from supergravity. So because for some solutions, for some special solutions of the strong constraint, double field theory exactly reduces to supergravity. And then we could perform some ODD rotation. And we would get some background which looks totally different. So, however, because we use the symmetry of the theory, this background should have the same physical properties. So we will not really learn something new here. It's a little bit more academical to study these transformations. So that bothered people, and so they wanted to come up with really something new, so with backgrounds with new properties. So, and they started to violate the strong constraint. So in a way which still allows for special backgrounds that the gauge algebra closes. And so they introduces a so-called closure constraint, and now something interesting happens, because now we can describe backgrounds which look very, very funny, like for example this guy here. So these backgrounds, for example, we call T-folds. And so they look quite strange from a geometric point of view, because they have a singularity here. So they identify a large circle with a very small circle while going along another circle. And so in normal geometry they are not well defined, but however for the string they are, because the string here propagates with some momentum excitations which are light on the large circle, and when it wants to change to this part of the background, it switches to a winding excitation. So we perform a T-duality here, so we patch this background with a T-duality transformation, and so that's why we call them T-folds. And they cannot be described with double field theory and the strong constraint. However, they are consistent with this closure constraint. And this is one of the few examples where we also know a full CFT description. So that's really a consistent background, and we can describe it in terms of asymmetric orbifold constructions. And the big plus of this background is that they have very interesting properties. For example, we can use them for get better control over moduli stabilization. So for example, Ralph Blumenhagen has did some work also how we can use this moduli stabilization scenarios to get better control over string inflection. So people are really interested in understanding these backgrounds because of their properties, and so that's why we want to go there. And these are called sometimes string geometries, because they really depend on the extended nature of the string. So they will not work for a point particle. Okay.
But I think you said strong constraints comes from string theory.
Exactly. So exactly when you do it on a torus, so that's why people are not really sure whether they are well defined, this kind of backgrounds or not. And so I will really show you how the strong constraint comes into the game, and I will also show you that one can relax it in a very, very well-defined way. Okay? Only to get this motivation. So, and I also want to give you some kind of another motivation for this kind of backgrounds in terms of gauge supergravities. And to this end, so I want to remember you that we looked at string theory, and that I have shown you that we can derive double field theory from string theory with this closed string field theory. And we can, of course, also get supergravity from string theory. And we can also get supergravity from double field theory with this special solution of the strong constraint. Okay, what do we next? So then we take the supergravity and we can compactify it without fluxes on a torus. So then we get a lower dimensional supergravity with much more supersymmetry. So, however, we could also switch on fluxes in the supergravity here without breaking supersymmetry, or only in a very controlled way. And then we get gauged supergravities, maximal or half-maximal gauged supergravities. There's also another way to reach this gauged supergravity, so we can use the embedding tensor formalism, which describes how we can consistently gauge this theory. So, and the interesting thing which now happens is we get a much bigger set of gauged supergravities than we can obtain directly from supergravity with flux formulations, flux compactification, sorry. And so exactly at this point, double field theories comes into the game. Because now we say, okay, we take double field theory, we violate the strong constraint, so otherwise we will land with Sucra, and this is not interesting, but we violate it and use this closure constraint instead. And then we also can access all these different gauge supergravities. And so when we have them, we can write down their equations of motion, find a vacuum, and this vacuum exactly corresponds to the background, to the stringy geometries I've presented you on the last slide. And so what we now want to do is, so we want to uplift them to double field theory. This normally should work, even if there are some technical ambiguities. So for example, you need for this generalized Church-Schwarz compactifications an object which is called twist. And people know its properties, but they are not really able to write it down for the most general setup. So there are some question marks here, but still people think you can uplift them to double field theory. But when we go a step further to full string theory, it becomes very, very complicated because, as you mentioned, we violated the strong constraint which we need to derive the theory in a consistent way. So, but still, as I already mentioned, there are some hints, but in general the story is unknown. And this is exactly what I want to change. And so I want to give you a motivation, what one can do differently. And to give you this motivation, I want to present you my elephant in the room. So there's a very, very big elephant in the room, which is connected to this flux picture. So because think about a very simple background with an H flux. So we switch on an H flux, and we solve the equations of motion of this background. And what we see, we will not get a torus anymore. So we get an S3. S3 with H flux is a well-known supergravity background. So, but now I told you, okay, in double field theory we have momentum excitation, and this we also have on the S3. So the string can propagate with some momentum, with some angular momentum in this case here. But, so what's now about the winding? So here the string can shrink to a point because we have no non-contractible circle. So we do not have any winding. So how can we then use double field theory? So, and the answer to this question leads us to a theory which is called double field theory on group manifolds. So, and we will see that this theory is a generalization of some kind of the normal double field theory. And we will also see that it comes with a new strong constraint, with a new action, and also with new symmetries. And we further will see that it solves this problem with the twist. So I told you they cannot really construct the twist in this generalized Church-Schwarz compactifications. And that it also will show us how we really can get this closure constraint in a natural way, and then how we can also treat this non-geometric backgrounds or the stringy geometries. So that's the plan. And so what we want to do is we want to derive double field theory not on a torus anymore, but on something more general, namely a group manifold. And so group manifolds have the big advantage that we, of course, still include the torus, because an abelian group manifold, so u1 to the power of d is a torus, but we can, of course, also now include the S3, so where we get an SU2. So, and these group manifolds have another very important advantage. We can write down a CFT description for them, which still is exactly solvable. So we can really do everything we want on the world sheet. And they can be connected to background with constant fluxes. So we are really seeing the impact of fluxes in the background. So still we want to have a double field theory, so we have to double it in some way. And I told you that momentum and winding are no options anymore, so because they are not well defined. So what shall we do instead? So, and the solution is quite simple, because now we can, of course, treat the left moving and the right moving factor of the theory independently. So, because strings are extended objects, so the left moving part can move differently from the right moving part. And so, what we get in this case also fits perfectly with the torus picture. Because when you remember string theory lectures, then you know that this momentum is only the sum of left and right moving, and they can also express the winding as a difference between left and right moving excitations. So using left and right movers is a very, very natural thing to write down a theory. And so we get indeed 2D independent coordinates. I will make this very specific in a moment. So, okay, now we really know what we want to do and what we are interested in. And so naturally some questions arise about the theory. For example, what are the covariant objects? Is it still this generalized metric, or do we get something completely new? Then, of course, how it is connected to double field theory, I already told you. So we should see that it is some kind of a generalization, but how does double field theory fit in? And so perhaps even the most interesting is, okay, I told you double field theory makes T-duality on a torus manifest. But on some non-abelian group manifold, we do not have abelian T-duality. So we should not get the simple ODD thing. We should get something more complicated. And so the hope, for example, is that we can make something manifest which is called non-abelian T-duality, and I think which is also much worse understood than abelian T-duality. Also from this point of view, it would be interesting.
Can you do this for any group manifold?
We can do it really for any group manifold. So we start with compact, semi-simple ones, but then you can also extend it. So I started to ask myself these questions, and I figured out that they are really not trivial. I was not able to, only from my physical intuition, to guess the answer to these questions. So what I have to do is I really have to sit down and try to derive the theory starting from a worldsheet perspective. And this is exactly what I would like to show you now. So, and to this end, I will start with some Western-Witt model, which exactly describes how a string propagates on a semi-simple compact Lie group. And so here is the sigma model for this Western-Witt model, and we have here some kinetic term which has a Keeling metric in it, and also this famous topological Western-Mino term which implements in some way a flux, an H flux, for example. And so we can interpret this Keeling metric when we apply it to the generators of the Lie group's Lie algebra as some kind of a metric. And so when we have a Lie algebra, we of course can look at the commutator of two generators, projection on another generator, and we get the structure coefficients of the Lie algebra. And so the structure coefficients are totally asymmetric with respect to all these indices. So we really get something which looks like a flux and which will be really a flux. And further, we can now study the symmetries of the theory. So, and we will find out that we have d-chiral and d-antichiral Noether currents. So, and d is a dimension of this group manifold. So, for example, when we have an SU2, so we have 3 chiral and 3 antichiral Noether currents. And these currents are exactly what will give rise to the doubled number of coordinates later on. So, and then we can take this currents, we want to go to a quantum theory, so we perform radial quantization, and at the end of the day, we get this OPE for the chiral currents, a similar one for the antichiral currents, and this is exactly the well-known Kac-Moody algebra in some strange normalization, which we choose to match it with the traditional double field theory formulation. Okay, so now we have everything we need, so we now can really write down a classic 3-level action starting from closed string field theory. And to this end, so we have to evaluate exactly this expression here. And the tricky thing in closed string field theory is that this expansion goes on and on and on for infinity. So it does not stop. However, so the higher terms, which have, for example, 4 of these string functions here, are very complicated to calculate. And so they are so complicated to calculate that nobody calculated them before. So that's why we are only sticking to these leading order terms, up to a cubic term. But this is okay, because this is exactly also the same which was done for traditional double field theory. And so first we need to know the string field here, and I've told you we have to consider only massless excitations. So what we are doing is we write down the most general massless excitation. And normally on the torus you would write down here a sum over all the different winding and momentum states, and you would act with some creation operators on this winding and momentum state. So for the group manifold there is no notion of winding and momentum, no natural one. So that's why here we are summing over all the different highest weight representations of the algebra of the group. So for the left moving and for the right moving part. So that's a new thing, summing over the different representation. And it really reduces to the sum over momentum and winding on the plate. And so finally, what we have to do, we have to write down the BRST operator, and we can do so when we look at the Virasoro generators, which we get from the Supergravity construction on the group manifold.
So are those higher order terms only supposed to introduce like higher derivative terms in that direction?
That's a very good question. Yeah. So normally we get an infinite tower of higher derivative terms in the low energy effective action. So, but what we will do on the next slide, so we will consider a special limit where we set the level of the Catenary algebra to go to infinity. And so this is like, again, when you think about the sphere, the level is connected to the radius of the sphere. And so you set the radius very large, and you go to some large volume regime where you suppress all these additional higher derivative terms.
Does that also suppress the higher order terms in the top line? Is that the expectation?
No. So these are different kind of couplings. So these higher derivative terms are connected to alpha prime corrections because so the volume of the sphere can be measured in string length units. These here are punctured in the worldsheet theory, and so they are counted by GS corrections. So this is a GS expansion, and the other thing is an alpha prime expansion. So, and we can treat them independently. But here we are really in some weak coupling limit from the GS point of view, like an ordinary.
Are you going to tell us the meaning of the comma, psi, comma, psi, comma, psi?
So
the definition of that operation, this cubic term.
This cubic term here? Yeah, so that's a very good question. It's a little bit more complicated because this is really goes to the basic of closed string field theory. So what you are doing is normally you consider, in a quite picturesque way, you consider a tree level interaction which looks like this. And there you put in all these fields here. So this is exactly the picture for this term. And then you have to calculate really this tree level amplitude in CFT, and you also have to make it compatible with the geometry of the worldsheet. So it's quite complicated to really calculate it in detail. So when you want to see this, I can show it to you. But this is the picture.
So in this talk, are you not going to worry about this psi cube term?
No, I'm worrying. I'm worrying about it. Yeah, but not about the psi to the power of 4 term, for example.
Yeah, but in the psi cube term, how do you define that object written in the first line? It's very abstract. I mean, there's
it's very abstract.
What's the meaning of that product?
Yeah, so it's really a scattering amplitude. So it's really in CFT. It's a scattering amplitude to see. So you can interpret this expression here in a sum over many different vertex operators. So you can really this is conformally equivalent to a sphere in CFT, and then you really put down the vertex operators at some points in, and then you really calculate the CFT amplitude. And here you also see that the moduli space here is trivial, because you have no parameter for the moduli space. So when you go to a higher, for 4-point interaction, for example, you would have to integrate over the moduli space. And to do this in a consistent way makes exactly this contribution so complicated. Okay? Okay, and now we also talked about a little bit about alpha prime correction and this k to the infinity limit. And exactly this limit now allows us to give some kind of a geometric picture or some geometric interpretation. Because what we have seen until now were all these abstract operators here in some Hilbert space, but we want to connect them with some geometric picture as in the standard double field theory. So what we are doing is we introduce a flat derivative, which is given in terms of a field bind contracted with a partial derivative on the coordinates of the group manifold. And this field bind is exactly given in terms of the left invariant Maurer-Cartan form of the group manifold. And then we can check that there is some mapping, so from this abstract operators to the flat derivative. So from the zero modes of the Catenary currents to this flat derivative. And we can see this, for example, when we remember the definition of a primary field in a CFT. So a primary field is an eigenstate of the Virasoro zero mode. So, and with the Supergravity construction, we can write them down as terms of this in terms of this currents, and we can translate them, these currents, in flat derivatives. And so we see that we also can interpret this state as an eigenfunction of this differential operator, which is nothing else than the Laplace operator on the group manifold. So we see that these abstract primaries are indeed eigenstates of the Laplace operator on the group manifold, and their conformal weight is exactly their eigenvalue. We can check whether this correspondence holds also for the algebra. So this is the Katz-Moody algebra for the zero modes. We get exactly this expression, and this is in total agreement with the one we get after switching.
So where is X tilde in this picture?
Very, very good. So I only look now at the left moving part.
Oh, I see.
I can do exactly the same for the right moving part.
Okay.
You're too fast for me. This is exactly comes now. So, but first, let's again remember we had a sum over all the different representations. We can map it here about a sum over all the different eigenfunctions. And this is exactly what the Fourier expansion. So when we are on the torus. So they're the eigenfunctions of the Laplace operator.
What is E over?
So this is some constant, you know, some constant, some coefficient which depends on R. So and so this is some expansion on the torus where the eigenfunctions are sine and cosine. This would be a Fourier expansion. And so this is exactly what traditional double field theory uses. It uses Fourier expansions. But here now we can also do it on a sphere where we get hyperspherical harmonics, and then we would expand in terms of hyperspherical harmonics or some other orthogonal function system. And according to what you have said, we have of course to do it also for the right moving part. So then we can double because we have D left moving and D right moving thing. We can introduce this doubled Vielbein, so we can also put this Keeling metric in a doubled object. And here we get two, so one with plus 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 signature and one with the ODE signature. We will need it later on. Okay. And now we come to the strong constraint. So this is really something important because you could say, okay, you did something wrong because you said you can treat left and right movers totally independent. That's not true. We know from closed string field theory that left and right movers are well connected by the level matching. So, and this is exactly what we have to impose. So we say that this operator here annihilates all the physical states. So, and also that's why it annihilates the spring field. And we can now write down with our flat derivatives this expression exactly in this form here. And this has to add on each component of the spring field. Remember, we had this epsilon there and this e's and so on. They were all parts of our spring field. And so I also gave you this eta metric. And we can now also write down a doubled flat derivative in the canonical way. And so we can write this expression in a very, very compact form. And this looks very, very similar to the strong constraint I've presented you. But we have to be a little bit careful because remember these are flat indices. And the other things were curved indices. So we have to go from flat to curved indices by using our Vielbein. And when we plug it in, we get an additional term. Because we are now not on a torus anymore. And so these guys can depend on the coordinates. And so one derivative acts on this coordinate-dependent object, and so we get an additional term, exactly this red term here. And the nice thing is that we can also state it in terms of the generalized dilution. So it perfectly matches into this formalism, so we can write it down in a very compact form and get exactly this additional term. And which is worth noticing is that we also can absorbs this additional term in some kind of a covariant derivative. At the moment, this is only something nice, but we will later on see that these covariant derivatives are very important in the framework of this theory.
Should I distinguish between the terminology of section constraint and strong constraint?
No, section constraint and strong constraint
in this talk. Okay.
Yes.
Just a little historical background. The fact that level matching in the CFT gives rise to this section constraint. Was that originally done by Siegel or way back, long ago?
I think so.
Okay.
So there are different formulations. So there's one formulation by Siegel, which is very important, and so one could also consider him as a father of double field theory. But he did not really call it double field theory, you know. And then came Olaf Holm, and Barton Süber and Chris Hall were the first. And they really did this closed spring field theory.
What does name call it? I mean,
and I think they also got the real interpretation with T-duality. I'm not sure whether Siegel really explicitly gave all this interpretation with the T-duality and this one. So that's what they gave.
But at least the level matching is a natural idea. It goes way back, right? Yes.
I would say so.
Okay, thank you.
And now what we can do, we can really calculate the action, and I do not want to give you all the boring details, only so far we have on the way integrate out some auxiliary fields, perform some field redefinition, and at the end of the day we again find some new terms. So exactly the red ones here. And so the other terms are the same as we would get on the toroids. And so you see that you, for example, get something which looks like a scalar potential. And this is natural because we are switching on fluxes, so we think that we should get some tree-level potential. So it's something which we expect. And so you also see when I go back to the torus, so to a non-abelian group manifold, these guys all vanish and I get the well-known result. So, and what we also can do, we can write down gauge transformations. So we can use again closed string field theories. We write down a string field for the gauge parameter. Again, a sum over all the different representations. And we do a lot of calculations. And at the end of the day, we get these bulky gauge transformations here, again, with this structure coefficient dependent terms which are here. So we have seen that we, going from the torus to the group manifold, we get new results for every essential ingredient of double field theory, for the action, for the gauge transformation, and for the strong constraint. Yes.
How is this approach different if you were to take the original, I guess the third 93 paper, where there's the heterotic strings being done, and you just forget about everything except the heterotic? How is that different from
it's a very good question. So that's what we also thought about first. So we were not sure what the level of the Katamuli algebra plays for a role. Because when you set it to level 1, you exactly get what you would get from heterotic string theory. So, but when you do this, then you freeze out all the degrees of freedom in the internal directions. You know, you cannot have momentums there anymore because they become heavy at this point. So this is really the extreme stringy point. But here we do this expansion in the level, so which really gives a new.
That was the thing that was related to the radius of the group.
Exactly. That was so. This is the parameter in which we do the perturbation theory. So, and this is also in one-to-one corresponding to alpha prime corrections. And so we really get a full dynamic theory and freeze not out anything. That's the idea here. But it's a good question. Okay. So sorry. You see all these nice results, and they are quite promising, but still they are bulky and unhandy. So we want to simplify them. Yeah.
Why are you using, can't you use just the flat currents and then attach the frames? Isn't that the easiest way to do it?
Yes, but we will see now, while we are rewriting it, only to use the currents is not enough, because the currents would give us some kind of a covariant derivative with only torsion but no curvature. So that's a left trivialization, normally. And this is also, this you get in this flux formulation of double field theory all over the place. But here we see that we get a covariant derivative which has curvature and torsion at the same time in a non-trivial proportion to each other, you know. And so that's why, but this you only see now when you rewrite it really in terms of the double indices notation. So then you really see the structure of the theory because everything condenses. So that's why I think it's not only right to only treat this flat derivative as the currents. There's more information in this theory, which we will see now.
Generally speaking, you should also introduce the connections, I guess.
Exactly. So exactly what we will do now. So you are too fast. You're too fast. We will now exactly introduce the connection. Okay. So but one step after another. First, we want to write it down in terms of these doubled objects, and I've already explained to you all these doubled objects or some of them. So we have this double generalized field bind with the left moving and the right moving part. This matrix here with the etas in it, flat derivative and partial derivative. We have all that. So we can also introduce in a natural way a double parameter for gauge transformations. And so we can look at the commutator of two flat derivatives, and we get another flat derivative. And so we have also a notion for the structure coefficients. And we can calculate it and get exactly these double objects. So this is canonical. However, there's one guy who makes our lives a little bit harder. So because these are the fluctuations here. So we also need a double version for them for this epsilon. And so they have two indices. So it's not a priori clear how to sort them really in a doubled object. And so I would like to give you exactly this suggestion here, how to sort them in. So which is symmetric, with respect to these two indices. And when we have a closer look at this object, we see that it is a generator of an ODD transformation. So applied on this ODD invariant metric eta, it leaves it invariant. So it's an ODD generator. And it has exactly the same degrees of freedom as this fluctuation which appears in the string field. So that's why it seems for us a natural way as a candidate for a doubled object. So, and all of you know when I have a generator, I of course can also write down a group element. So using the exponential map. So, and this is another advantage of this, because now we can extrapolate to all orders in these fluctuations, because this group element really not only captures the linear part and the quadratic part, but it goes on for the cubic part, and it goes on and on and on to infinity. So that's why we can lift our results in the cubic part. So you have seen this cubic string functions to all orders. So extrapolated. Yeah, so it's something.
Well, only if you're lucky enough to have this combination.
Exactly, only when you have
extrapolation.
Exactly. So, well, we will see that we are very lucky, because normally the gauge algebra should not close when I extrapolate to all orders. But it does here in this case, because I have this very heavy structure, of course, of a group manifold with extremely symmetric and so on. But it does. And so this has exactly the defining properties of the generalized metric. It is symmetric with respect to these two indices, because the generator is, and it leaves the eta metric invariant. And now we want to write down generalized Lie derivative in the same way as we have for double field theory. So where we express gauge transformations in terms of this generalized Lie derivative, and we take the same ansatz as for normal double field theory, only with this flat derivatives instead of partial derivatives. And we, of course, also have to add the structure coefficients, because remember, they were the additional part which we found, so we have to implement them in some way. And then we can check, so do all the calculations, that when we assume that this metric here is not affected by the gauge transformation, and this is natural because it's some kind of a background object and not a fluctuation, then we can really check that we can write down the gauge transformations for this epsilon I gave you 3 slides ago in terms of this generalized Lie derivatives. And with the expansion of the eta metric, we really see that this generalized Lie derivative on the generalized metric really gives us the results we want to have up to the order we have calculated. So we can really make a perfect match up to this order. And we can do exactly the same for the generalized dilaton. So, and now I want to show you exactly the thing with the covariant derivative we talked about. So, because now it's nice to absorb this f terms and this flat derivative terms, so to combine them in a covariant derivative. And so we exactly get this covariant derivative, and when we now rewrite the generalized Lie derivative from the last slide, then we get exactly this expression, which looks nearly the same as in traditional double field theory, but we have to exchange the partial derivatives with these new covariant derivatives. So that's it. Yes?
For the ordinary leader, it doesn't matter what connection.
Exactly. So exactly. Here it matters. So it's a very good question, and I left this slide away because I thought it was too technical. But so what you normally have, you have the torsion in the normal Lie derivative, and when it's torsion-free, it does not matter. And for the generalized Lie derivative, you have the generalized torsion, and the thing is, this new connection has a non-vanishing generalized torsion. So it really matters that you have here a covariant derivative and not a partial derivative. Perfectly right. Thank you very much.
What the commutation relation with Manifolds? Because I thought the D's already had the F in it. Didn't you tell me?
So the D's?
Torsions? Yeah.
No. They are really only the partial derivative constructed with the generalized Q-line. So they do not have the F in it.
Oh, then I just misremembered the previous thing.
Yeah,
Okay.
sorry. But
So the nabla has the F. Nabla.
So the nabla?
Yeah.
Yeah. So this is nabla. The commutator of nabla gives me the torsion and the curvature of this covariant derivative. And we see that the torsion is exactly, again, the F, and so it also has a non-vanishing curvature. I can show you the details.
So you have introduced a connection, effectively.
But
there's not a unique procedure. There could be many.
Very
why have you decided on this one?
Great question. You are totally right. I can introduce a bunch of connections on a group manifold, with curvature, without curvature, everything. And this one is a quite strange one, because it's not at all the canonical one. So the canonical ones are Liberty-Vita connection, no torsion, but curvature, and the left and right trivialization, which have only torsion, but no curvature.
The paralyzing torsion.
Exactly.
Which makes curvature 0.
Exactly. So
is that the one you have now?
No, it's not. It's a special one. It's a one which you never have guessed. But the closed string field theory forces you to exactly write down this thing.
Uniquely.
And the other thing which is interesting is, now when you look at the closure, so I will show you on the next slide, let's perhaps discuss this first. So we of course now want to see that this new gauge transformation closes. So we can write down again the C bracket, and so then we can look whether this fulfills the Jacobi identity. So, and we do this again, closed string field theory, write it down and see again, oh, we get again covariant derivatives instead of partial derivatives, so we get now everywhere covariant derivatives, and we also got them for the strong constraint, remember. So, and now we can check whether this closes or not. And we find that it really closes when we apply for the fluctuations the strong constraint, but for the background we only have to apply the Jacobi identity, because we are on a group manifold. Of course, the background structure coefficients have to fulfill the Jacobi identity. And this only uniquely works for exactly this connection. When I would choose another connection, nothing would close anymore. So I can write down, I could also approach this from another way. I could write down an arbitrary connection and say I want this guys to close, and I would get exactly the same connection which I got from string field theory. But I would have never guessed it.
When you say string field theory, your computations amounted to 2 and 3 point functions. That's
exactly.
it. That's enough.
But yeah, that's enough to give me this structure, and I can really extrapolate it to all orders in the field.
Well, that's a conjecture.
No, but I see it with the closure, you know. I really, for this closure calculations, I use it in all orders in the fields because I applied it to the general estimate, which is really a group element.
Are you predicting 4 point functions in this way?
Yeah, that's a very, very good question. So you could say you could predict 4 point functions in this way. But normally, what closed string field theory tells you is that the 4 point function should not close off shell anymore. They are not forced by closed string field theory to close off shell. They are only forced to close on shell. So it's a little bit brave to say we really get all the possible results. So what we get is something which is self-consistent and works up to tree level. Okay. So the other thing is a little bit more tricky. But in general, you could say...
You mean 3 level or 3 point?
3 points. 3 points.
Yeah.
And everything which comes beyond this. So because we also have all thrown away all the massless excitations and so on, we did a lot of simplifications. But still, it works, you know. And yeah, so the important thing that we come back to this is that we have the strong constraint for the fluctuations and this Jacobi identity for the backgrounds. And this is exactly the closure constraint I gave you, this Jacobi identity, because it's much weaker than the strong constraint. So that's why we get all the stringy geometries at this point.
You still have to impose the strong constraint.
For the fluctuations, but not for the background. And this is the important thing. So for the Schwarz compactifications, you put some ansatz for the background. And there you, of course, in normal double field theory, also have to impose the strong constraint. But here, because we have the direct distinction between background and fluctuations, so we have this much weaker constraint for the background, and this is enough. When you do not want to get the full Kaluza-Klein-Teil in the conductor. Okay, and now we can write down the action. So let me go a little bit faster. So we get the integral over the double space with left moving and right moving coordinates. We get again a generalized dilaton. We get this generalized curvature scalar, and again we get covariant derivatives all over the place instead of partial derivatives, and we also get an additional term here.
This is Ricci scalar you've written here.
The generalized Ricci scalar.
I was told by my friend Olaf Holm that nobody knows how to write curvature tensor.
Yeah, exactly. So
is that still true?
Yeah, that's exactly true, because Olaf uses another notion of covariant derivative. So he wants to write down a derivative which is covariant with respect to the generalized Lie derivative. So that's the ODD covariant derivative. And this one is quite ill. So because it has not well-defined connections and so on, it's
the
quite
one he is
complicated.
trying to use.
Yeah?
The one he is trying to use.
Yeah, exactly. So this one is a different one. So it is covariant with respect to normal diffeomorphisms, to 2D diffeomorphisms, which also gives us an additional symmetry of the theory. So we will see this on the next slide.
So can you write the Riemann curvature tensor? Can you write?
I can write it down
can.
for the background. For the
For the
because
background.
I have really now I have two different objects, you know. I do not want to make them all the same and treat them on the same footing, but I really distinguish between background and fluctuations. And my background is now totally geometrically. And I can write on curvature, I can do all fancy things with the background.
And it's in 2D dimension.
It is in 2D dimensions, exactly. It's in 2D dimensions. That's an important thing. Yeah. And so these covariant derivatives exactly correspond to the background, and they are completely geometric.
But you can always take the toroidal limit of the group manifold,
Exactly.
right? The maximal torus business.
Exactly.
Shouldn't you then derive results?
Yeah,
relevant
then
to-
I get exactly what I've results. Because remember, so the connection depends on the structure coefficients. When I go to the abelian case, the structure coefficients vanish, and I can write down the partial derivative.
What you said, you have a curvature tensor, which it doesn't. So if you take
Exactly.
the limit.
Yeah, but on a torus, I do not need the curvature tensor because the torus is flat. You know.
Oh yeah, you are doing background. Yeah. Okay. Okay.
I'm doing the vector.
Okay.
And now you also see this eta metric here, which is now connected to the background again, is not constant anymore. It depends on the coordinates, and I use it to contract everything. And so I also have this metric for the background, not eta, but this one with a positive signature, and this is exactly the one which appears in the generalized diatom. So, and I define the covariant derivatives exactly as one would do with these Christoffel symbols, which I can calculate for my flat covariant derivative by assuming compatibility with the frame field. So I can really calculate everything which you see here from the background information. So, and then I can check again the symmetry. We have seen this generalized Lie derivatives on the generalized metrics, the same for the generalized dilaton as in normal double field theory. And they are closing when the strong constraint holds, and this assumption for the backgrounds, the Jacobi identity. And I also get 2D diffeomorphisms now, because my background is completely geometric. So I can have this new 2D diffeomorphism symmetry, and they do not depend on the strong constraint. And I can check now the covariant objects are really these objects I gave you in the action, which transforms as a density and a scalar under both these symmetries. So I also get this new symmetry. Okay, so let me now come back to the point where I started. So we now use string theory. We derive double field theory on group manifolds with closed string field theory. And now we can, of course, again go down here and do this reduction. And we can still apply the strong constraint for the fluctuation, it's fine. But we apply the Jacobi identity for the background. And this is exactly the closure constraint. So we get all the gauged supergravities here now. And we also do not have the problem with the twist anymore. Because like in normal geometric Schwartz compactifications, the twist is now the left invariant Aura-Cartan form. So this works. It does not work in traditional double field theory. There it goes wrong. Here it works. And so we can really do this compactifications in a very, very explicit way, get all the gauged supergravities. I do not want to show you any details. And then we can solve the equations of motion. We can lift it up to double field theory on group manifolds. But here now, we did not violate any constraint. So we could also try to lift it up to full string theory. At this point, we have to be a little bit careful, because all the calculations I've shown you were tree-level calculations. I do not include any loop-level calculations. So when this uplift also seems possible, it seems possible at tree level. Loop-level things give me additional constraints, which could, of course, spoil against this uplift. So, and I only want to give you a very, very short example. So I want to give you an example with 3 internal dimensions. So I want to look at an embedding into O3, 3. And there are 12 different ways to embed in this half maximal electrically gauged supergravities. And so there is a table there classified in this nice paper here. And so I only want to choose one, which is parameterized by a real parameter alpha. And then I can really write down the structure coefficients, which are in one-to-one correspondence to the generalized fluxes in this background. And you see this alpha exactly gives me some kind of an asymmetry between left and right movers. This is what this parameter is doing. And then I can check whether this works in double field theory. And I see the strong constraint is violated always when this contraction does not vanish. And I see, so I can only fulfill the strong constraint for exactly one point in this orbit. So for all the other points, I cannot apply normal double field theory. However, the Jacobi identity always holds. So that's the idea behind the embedding tensor. So I can always apply double field theory on group manifolds. And so what I'm left with is exactly this picture here. So I get now an orbit of backgrounds which cannot be treated with normal double field theories, which are in this regime of string geometries. At this one point where alpha equals to 0, they touch the border of double field theory plus strong constraint. And then people say, okay, now I can perform an ODD rotation, so to get something which is an S3 with H class. But still ODD rotation here, the people call it T-duality, but it's a little bit more complicated because on a torus it would be a T-duality around all internal directions. But take a T-duality around all directions of the sphere. That's not a abelian T-duality anymore. That's a non-abelian T-duality. So even at this point, it's not so easy to say. However, so we get this orbit here, and we have to be careful again, because for the simple case of SU2, so the S3 I've shown you, we know that there's only one setup with a modular invariant partition function, torus partition function, and so this rules out all these backgrounds here at the loop level, however, on the pre-level blocks. But people are quite positive that they find for more complicated groups that they find examples where we also get some consistent, torus partition function. Okay, so that was it. So that was the story I wanted to tell you. And so I think the take-home message is that we really found some kind of a generalization of double field theory. And so the basic idea we followed is to go beyond the torus case. So also consider group manifolds. So because we were able to do the calculation also for group manifolds. And so we got, in doing so, some modified strong constraint, some new symmetries, so this geometric symmetries for the background, and also a new action. So we are now able to treat this really non-geometric backgrounds in a more consistent way, and also are able to construct the twist of this generalized Jerk-Schwartz convectifications. And so there's another point I could not show you because I did not have the time, but we can also show that double field theory really comes out as some special case of the theory, also when you put into something which is called extended strong constraint. And so finally I want to tell you some open tasks. So of course we now have to find some solutions for this new strong constraint, which should be different from the standard solution of the strong constraint. And this is also perhaps the idea to really understand how T-duality is implemented in this framework. So this is what I'm working on at the moment. And then one also could, of course, try to study alpha prime corrections, which are connected, as we already mentioned, to this 1 over k, to the radius of the sphere. And so this alpha prime corrections also seems to be richer here than in the normal toroidal double field theory, because at sub-leading order of alpha prime, the string starts to probe the curvature of the space. So when you really start to calculate alpha prime corrections in this setup here, so I started to calculate them, so you get a bunch more of alpha prime corrections than you would get on a torus. So, and another way to extend this formalism is also to look at some coset or orbifold CFTs, which are still doable, like the one for group manifolds, and check what comes out there. Okay, so that was it. Thank you for your attention. And we have a lot of questions already, so are there some additional ones?
I'm just going to ask you the same question again, so you guys should probably go first.
We'll spare you, because we asked you a lot already, so we won't make you suffer any further.
No, it was fun. It was fun.
I mean, the philosophy behind double field theory business, I mean, at the end of the day, is it rewriting of things we would be able to write anyway, or is this something beyond that? Suppose I didn't know about this geometry, but I know how to deal with CFT on group manifold very well. Yeah. I could go and compute things as needed. Yeah. What is the gain if you, you know, I'm sure there are gains. This is not a skeptical question, it's just that to probe it.
Yeah. I think so. So I think the gain is really so you know you have much structure in the CFT. So you have a very, very rich structure in the CFT. Mm-hmm. However, I think you want also to learn something from the CFT for field theories. So because string theory, so the CFT description has an infinite number of states, you have to truncate it in some way and so on. And then this is the magic of string theory. You know, you start from a CFT which does not look like gravity at all, and then you really, as effective theory, you get Einstein, Hilbert action, and so on. And the thing I think here is something similar. So we really want to understand the underlying symmetries of string theory from a field theory point of view. So I think this is what double field theory is trying to do. Of course, you could do all the calculations in the CFT, but there's also the problem that you, for example, for some Calabi-Yau spaces or something like this, you are not even able to write down a CFT.
Yeah, but here it will be the same problem, right?
No. Here you look at, here you can describe some fluctuations around this background. So you have some kind of background, and then you start to fluctuate around this background, and then you can flow away from this background and can probe the near environment of this background. And that's also the case why I think that double field theory, which was derived on a torus, cannot work for a sphere. Because, of course, you can take a torus and with small fluctuation deform it a little bit, but you cannot change its complete topology by small fluctuations. So that's why I think here something new has to come out, you know. But still, it's like supergravity. Supergravity is background independent, you know. It does not really need the thing that we put in, that we first start with a free CFT on a flat space. So, but then we can flow away from this point and get a bunch of other CFTs in the large volume limit, which we did not have before.
Okay, thank you.
Why do we keep, so it looks like historically we started on the world sheet, then we started talking about target space and doubled and then confused ourselves completely because it really shouldn't be doubled, other than the fact that the string has left and right movers the way it started in the first place. Why are we just going back to the original world sheet and trying to implement the symmetries there?
So again, I think we really want to have some effective field theory description, you know, to start to study more complicated setups, so to use all this power, for example, of compactifications, or all this geometric power to do so, you know, to study these things. So we really want to have a bigger toolbox. So because you are quite limited in the CFT, you know, in the CFT language. So you can only write down CFTs for very, very simple models. And so again, so to make my point more clear. So what we are here doing is we flow away. So you could also describe it as a conformal perturbation theory, you know. So you make some deformations, so and you try to find marginal operators to flow away from one vacuum to another vacuum. And this is exactly what you do here. So for example, you get a scalar potential. The scalar potential has flat directions, and then you can flow along this flat directions from one background to another background. This is a marginal deformation. And so you can start with one CFT, and so go to a whole family of different CFTs. And the thing goes much further, and I think this is what Barton Zwiebach and all these people wanted to do with closed string field theory, when you really can write it down to all orders in the fields. So then you can start with one particular background, and then you can flow away from this background, and you can get all other different backgrounds which are there in one theory. And this would be a dream, making string theory background independent. So, however, it's much too complicated. And one thing in double field theory is when we try to understand T-duality, and when we could give a non-perturbative formulation of T-duality. So, for example, this alpha prime expansion. you know, so you have this S duality, and there's GS, the parameter, plays an important role, you know, the string coupling. So when you can use this to write down theories which are non-perturbative in GS. So it would be great when we could do this for T duality, when we have something which is non-perturbative in alpha prime. And so then we have learned much about the symmetries, and we get a much better label also on background dependency. But this is far away from happening, you know. That's what people are dreaming of. At the moment we are in leading order alpha prime, and we can handle the torus, and so I hope we can also now handle group manifolds in the leading order of alpha prime. So that's the
Will you be here tomorrow?
Yes.
And any further than that?
No. Tomorrow
Only
and the
day.
day after tomorrow, my flight is going in the
Okay.
afternoon.
So you have one more day during which we can pester you.
Yeah,
Okay.
yeah. I would love this.
Good.
Okay.
Thank you.
Thank you.
Okay.
Thank you.
Tell me again what the strong constraint is. What is the closure constraint?
Yeah.
What is that?
Right, that was also
No, sorry. Yeah. I would love to.
I'm not saying down this option.
Yeah, that I can show you. So the closure constraint is something